Okay, so let's start with the second lecture for week 13. And you should have gone over an introduction to the digital and analog domains and the conversion between them. So for this lecture, yung focus natin will be the analog to digital na conversion. So recall na from the last lecture, mapping operation lang naman ang pag-convert to analog to digital. But ano ba yung circuitry na kailangan natin to actually accomplish that? So that will be covered in this lecture. So yung general operation of an ADC na circuit level, and then types of ADCs. So we'll be covering two types of ADCs. So basically implementation ng analog to digital na converter. So an analog to digital converter needs to do two things para makakuha ng digital signal. That is sampling and quantization. So sampling is defining the signal at specific time points, and quantization is representing information with a finite set of bits. So recall ang ating digital signal ay quantized in both time and level or voltage level. So for example, we have a sinusoid here. Para i-convert to digital signal, we first do sampling. So let's see, medyo preview to. So sampling, we get the voltage at specific points. Ayan. So kung wala ito yung zero line, we get specific points dyan. But yung ating voltages na makukuha dito can still range from yung full scale to zero. I mean, infinitely many values pa rin yan. So what we do next is quantization. You know, kuha nating values dyan, i-map natin to our fixed digital values. So kung wala ito, i-assign natin ito as 0, 1, ito si 1, 1, ito is 0, 1 din. So let's say na may konting difference dyan, but because of quantization, we get the same result. So for example, ito si 1, 0, 1, 0, tapos ito is 0, 1 again. So yung essentially yung bulk, yung actual analog to digital na conversion is actually this process, yung quantization, which is sometimes yun yung ginagawang synonymous na terms, yung quantization and analog to digital na conversion. But ang ating analog to digital na converter does both of these. So moving on, sampling muna tayo. So in sampling, we usually have what we call the sampling frequency, or gano'n natin kadalas isample ang ating signal. So yung mga square na to, yun yung mga times na sinasample natin yung signal. So for example, this is a 101 kilohertz na signal and we are sampling at 1 megahertz. So excuse me. Ang isang signal period natin, yun, and then 1 megahertz yung frequency ng ating samples. Then meron tayong tinatawag na Nyquist frequency, which is twice the highest frequency of the input. And this is usually what is considered as the minimum sampling frequency. So bakit siya yung minimum sampling frequency? So let's say here, meron akong dalawang signal, 101 kilohertz and 899 kilohertz. If sinample ko sila pareha at 1 megahertz, kung titignan lang natin yung mga square dots na yan, essentially the same signal yung nakuha ko to both of these. So disregarding yung kung ano man nangyari in between samples, kasi pag digital signal tayo, yung actual samples ay yung kino-consider natin. So for our signal here below, ang masustore na signal natin is itong signal na ganito pag ni-reconstruct natin siya. So this is because ang ating sampling frequency is less than twice ng ating input frequency. Nagkakaroon tayo ng possibility of tinatawag nating aliasing. So meron tayong dalawang signal, magkaiba sila, 101 kHz, 899 kHz. But after sampling, they look the same. So yun yung tinatawag natin aliasing. So in order to avoid this, we sample at the Nyquist frequency or higher. So, then next in sampling is what we call sample and hold. So ang ating sampled signal is maintained for a given period to give the ADC time to convert the sampled signal. So hindi enough na makuha lang natin yung signal at this point, hino-hold natin siya for the conversion process. So makikita nyo naman later bakit natin kailangan i-hold yung signal. Kasi ang conversion from an analog signal to a digital signal is not instantaneous. So kailangan ng time na i-hold yung ating sampled na input and doon yung time na process tayo. So ayun, yun ang sample and hold. Hopefully ma-appreciate ito more later on. But ayun, yun lang naman for sampling. Usually, at a constant uniform rate tayo na sampling frequency. There are cases na hindi, but those are for special applications. So next we go to quantization. So quantization is actually yung ating mapping operation itself. So ideally, we want it to look like this. So pag yung itong nasa baba yung analog input, if within if you recall, delta is yung ating 1 LSB or yung minimum voltage step. So this is VFS over 2 to the N. So in this case, yung ating N is 3. So 3 bits yung digital output natin. So 2 to the N is 8. So VFS over 8. So pag example, 1 volt yung 1 volt ang ating VFS, 1 over 8 siya. So ito is 0.1825 volts. Is 0.25 volts. So anything between 0.125 and 0.25 volts, ito yun, mamamap siya to actually hati pala. Anything between halfway ng 0.125 to 0.25 at saka halfway between 0.25 and 0.375, siya yung mamamap kay 0101. So ito yun. And then pag dito naman yung range of values, mapupunta kay 0111. So yun na yung mapping natin. So essentially ang method ata dito, pag fractional part is find the nearest integer. So find the nearest integer siya. Kaya siya ganyan. So we have a couple of extra terms when it comes to convert in terms of quantization. So first is what we call offset. So yung green ba to, yellow? Yung yellow line, siya yung meron tinatawag na offset and negative offset, which means na hindi naka-center yung ating conversion. So basically parang nag-add or subtract tayo dun sa analog input before tayo mag-convert to the equivalent na digital output. So meron tayong offset. So parang, ayun, if convert mo yung 001, hindi na siya masyadong tatapat sa 1 delta ng value. So yung offset. Then, we have what we call linearity, which describes yung ating transfer characteristic. So being linear means for every step, equal yung spaces natin for each digital output. So in a nonlinear na converter or quantization, makikita natin dito, yung mga digital codes natin dito sa gitna, yung range of values niya, maliit lang. And kung titingnan natin yun dito, sa taas, mas malaki yung range of values na namamap kay 110, for example. So yung range of values niya is from here hanggang here. Yun na mamap kay 110. So mas malaki yung, mas maraming analog values yung namamap kay 110 compared kay 100. And that means it is non-linear. So linear tayo pagka pantay-pantay lahat. Okay. Then, yung tinatawag natin quantization error, which is yung difference ng ADC output natin from the ideal na converter or analog data. So basically, ano yung difference ng ating ADC input doon sa equivalent na digital output na code. So you can see here na pag saktong 1 delta yung ating input, nasa 0% error siya kasi sakto siya. Pero pag lumalapit tayo sa, kung dito, 0.5 delta, doon nakukuha yung maximum na quantization error. So, you'll see na pag non-linear yung ating converter, maaaring dito sa gitna natin, mas maliit yung quantization error niya. Siguro parang hanggang dito lang, hanggang dito lang. And then, pagdating dito sa mga sa labas, is lalaki na naman yan. So basically, if we're expecting na marami tayong inputs dito sa area na to, we can give more digital levels para dun sa inputs na yun para bumaba yung overall quantization error. If madalang lang naman natin nakukuha yung nasa extremities, so madalang lang makuha yung mga malalaking quantization error, effectively yung on average, mababa yung quantization error natin. So, yun yung dating dalawang steps, sampling and quantization and related terms. So now let's look at yung ating mga certain implementations of an ADC. So ito yung mga types, well, based kay ating reference, kina Chen and Broderson. We have 1, 2, 3, 4, 5, 6 types of ADCs na based sa kanilang mechanism to make the quantization. So you can see here, we can get fast. So yung bandwidth natin basically means yung top frequency na pwede nating makuha signal. Meron tayong mabibilis na ADCs dito, pero ang kanilang resolution ay medyo mababa, mga 8 bits. And we have high resolution na ADCs na umabot ng 24 bits, pero mas mababa ang kanilang resolution. So you can see here na parang merong diagonal line dyan na parang pumipigil sa atin na hindi tayo pwede makakuha ng mataas na bandwidth and mataas na resolution. So parang meron tayong natawag na trade-off between the speed and accuracy of our ADC. So much like in life, merong mga trade-offs yung mga ginagawa natin. Kung masyado nating binilisan, may mataas yung chances na magkamali tayo. And if masyado naman tayong, if pag-isipan natin ng konti, bagalan natin ng konti, kaya natin maging mas exact. Pero we can't be exact and fast at the same time. So I guess itong mga pipeline ADCs, yun yung mga mahihirap gawin. Tanong nyo lang yung mga iba kong batchmates. So let's go with actual circuit implementations of ADCs. So if we have a simple 1-bit ADC, that is just what we call a comparator. So kaya mo itong gawin. So yung sampling natin can be accomplished with a flip-flop. So ang ginagawa lang sa comparator is meron tayong reference signal dito. So actually kaya mo itong gawin with an op-amp. May reference signal lang dito, i-compare natin dun sa input signal na Vin. If mas mataas si Vin kay Vref, digital signal natin is high. Pag mas mababa si Vin kay Vref, ang digital signal natin ay low. So basically, pwede mo isipin if VDD is 1 volt, pag si Vin mo sa taas kay 0.5, digital 1. Pag mo sa baba siya sa 0.5, digital 0. So an improvement or yung next step natin from the comparator is what we call a Schmidt trigger. So ang ginagawa sa Schmidt trigger, meron tayong dalawang threshold. So in order for the output to transition from VDD to V, so inverting pala to, no? So it needs to reach a certain voltage bago mag-transition. And para mag-transition pabalik, iba na yung threshold na kailangan niyang i-meet. So bakit niya ginagawa yun? Let's have an example here. If meron tayong single threshold, kamukha dito, once na bumaba siya ng konti, kahit na in-expect natin na mag-maintain high yung signal, magkakaroon ng trip or magkakaroon na parang glitch dyan sa ating input. So, very common to pagka maingay yung signal or noisy yung signal. Then, medyo mas malala dito sa part na to. So, parang nag-alinlangan siya bago umakyat. So, nag-alinlangan din yung output ng ating digital na circuit. So, what we would want is a more solid na signal. And what we can do is implement a Schmidt trigger na pagka-trip niya sa taas, kailangan niya ng mas mababang signal bago mag-trip pababa. So kahit na bumaba siya dun sa original threshold, mamaintain niya pa rin yung high value niya, and yun din sa kabila dito. Hindi siya agad magta-transition to high basta ma-cross yung ating threshold. So because of this mechanism, it is also called the noise resilient na comparator. So kahit noisy yung signal natin, hindi agad magtitrip yung ating signal. Then, ayun, to extend yung 1 bit natin, yung regular na comparator, isa lang yung reference na kino-compare, we can extend it to multiple comparators with multiple different references na kino-compare. And of course, pwede mo namang gawing Schmidt trigger yung mga to. Pero mahirap na siyang design masyado kasi yung mga trip points kailangan nasa certain levels and etc. etc. So basically, ang flash ADCs ay maraming comparator na iba-iba yung reference voltage. So essentially, itong ating resistor ladder dito, siya yung gumagawa ng digital equivalents ng ating code. So pag mas mataas ka kay 1/4 VREF, ibig sabihin nun, 01, digital code 01. If mas mataas ka sa 1/2 ng VREF, digital code na 10. If mas mataas ka sa 3/4 ng VREF, digital code na 11 or 3. So parang this is a 2-bit ADC niyan. So essentially, naging equivalent nito is pagka below 1/4 VREF ka, digital code 00. Pag below 1/2 and above 1/4, 01. And then pag between 1/2 and 3/4 naman, 10. And if above 3/4 ay 11. So 2-bit. So meron tayong 4 distinct na stages. So ano yung, so yun, mukha simple, madali lang gawin. Kaso what if gusto na natin ng 3 bits na flash ADC? So kailangan natin ng 2 to the n na resistors and 2 to the n minus 1 comparators. So kung gusto ko ng 10-bit na ADC, kailangan ko ng 1024 resistors. So para medyo mahirap gawin yun, no? So a flash ADC, usually ginagamit lang to for role-less solution. And yun nga, since mukhang madali lang, parang isang stage lang yung kailangan daanan. So mabilis siya. So kung babalikan natin yung graph natin dito, ang flash ADCs, nandito siya sa baba. Mataas, kaya nyo ng mataas na bandwidth. And kaso yun nga lang, hindi tayo makakagawa ng masyadong malaking resolution na flash ADC. Kasi exponentially nagsiscale yung ating devices. So, ang ginagawa ng flash ADC ay kino-compare niya yung ating input with several different reference voltages ng sabay-sabay. So what if gawin kong isa-isa muna? Like here, dito sa counter ramp ADC. So yung reference voltage ng ating counter ramp is sourced from a DAC or a digital to analog na converter. So instead of a resistor ladder here, meron tayong reconfigurable na DAC na pwede natin gawin. At the start, ang ipapa-input natin kay DAC 00 and i-compare natin kay Vin. And then at the next cycle, so may clock to, at the next cycle, increase natin yung digital value and mag-increase yung analog output ng DAC. Lalaki yung reference dun na kino-compare si Vin. And ayun, check natin yung output. So eventually, makaka-reach tayo ng point na yung digital output natin dito, mas malaki na siya kay Vin. So yung output ng ating comparator, mag-flip na siya. So, ayun. Basically, dito pumapasok ang sample and hold na circuit kasi kailangan nating i-hold yung output for this amount of time para doon sa conversion. Pero yun, siguro, you can say na instead of using 2 to the n resistors and 2 to the n minus 1 na comparators, we can just use one comparator, a single DAC, and several clock cycles naman to finish. So basically, instead na sabay-sabay with a lot of components, isa-isa with more time. Pero yun nga, it takes a while to finish. Kung dito, meron tayong 2 to the n na resistors, dito meron tayong 2 to the n na cycles bago siya matapos mag-convert. So one cycle needed for each code dun sa DAC or dun sa ADC natin. So ano yung improvement dito? So you can notice here, para tayong nag-linear search. Nag-isa-isa tayo from the lowest to the highest. So what we can do is make a binary search, which is yung ginagawa ng sinatawag na Successive Approximation Register ADCs or SAR ADCs. So may register pa dyan. May natawag na tayong Successive Approximation Control Logic. So parang binary search. Instead of mag-start sa pinakadulo, mag-start tayo sa gitna. And if mataas siya dun sa nasa gitna, edi dun tayo mag-search sa upper half. If mas malaki siya, mas maliit siya, balik tayo doon sa lower half. So basically, hinahati natin yung search space natin. So basically, after the first cycle, we say the input is over here. After the second cycle, the input is over here. After the second cycle, the input is over here. And so on and so forth. So, makikita natin dito ang ating processing time instead of 2 to the n is just log na 2 to the n or O of n. So kung ilan bits yung ating or ilan yung resolution ng ating ADC, ganun din kadami yung mga cycles bago siya matapos. So we can have an example here. So for example, si 3.2 volts, gusto nating ma-convert to a digital code. So we start at the middle. So yung DAC code natin is 1000. So this is a 5-bit na ADC. So yung 1000 is 2 volts. So mas mataas siya. So we keep that 1 here for the next cycle. And then we get 1100. Yung equivalent na DAC is 3 volts or the equivalent na signal. So we continue growing our DAC value. So dito naman 1100 or 3.5. So mas mababa siya. So for the next cycle, may kita mo dito, yung 1 na initially natin nilagay, tinanggal natin, ginawa natin 0 kasi mas mababa siya dun sa line na yun. Or mas mataas yung digital output or yung analog output ng DAC dun sa digital na input. So after nun is co-compare siya sa next stage since mas malaki pa rin yung digital equivalent is ayan, yung 1 dito may 0 sa next stage. And ito, since yung ating signal is mas mababa, we actually retain yung huling 1 dito. So yung ating ADC result ay 11001. And ayun, so that is yung ating SAR ADC. So yun na yung itatakal actually natin na types of ADCs. And then we have a little bit more notes. So maraming ADC na pwedeng pagpiliin. So ano yung dapat natin consider pag pumipili ng ADC? So first of all, you will need to know yung conversion time mo. Kailangan alam mo yung application kung saan mo gagamitin yung ADC and alam mo yung maximum frequency ng expected na input. And then we are also limited by our microcontroller capabilities. So faster conversion would usually require more power, and if hindi kayang mag-supply ng power ng iyong microcontroller, hindi gagana ng maayos yung ADC. And additionally, if mataas or mabilis yung conversion time, kailangan mo ng mabilis na clock signal na baka hindi kayang gawin ng microcontroller. So after you know your conversion time, that will generally mean may kita mo na kung saan ka lulugar. If kailangan mo ng mataas na conversion time, usually mas-stuck ka with low resolution ADCs. Pero if mababang resolution na naman yung kailangan mo, pwede ka magtaas ng if mababang speed lang naman kailangan mo, pwede ka magtaas ng resolution para ma-accurate yung inyong measurements. Pero yun nga, higher resolution means lower quantization error. Pero if masyado namang precise yung ating ADC, baka nagsasayang lang tayo ng power. For example, ang ADC natin 16-bit with a reference of 3.3 volts. So yung 1 LSB natin or yung 1 delta natin is 50 microvolts. So every 50 microvolts, ibang ADC value siya. What if yung noise natin 1 millivolt yung amplitude? So ibig sabihin nun, hindi natin magagamit yung isang LSB natin kasi yung 50 microvolts na yan, it's just representing noise. So it's not representing information. So when you consider your system, kung 3.3 volts lang yung reference mo, it might not be a good idea to get a 16-bit ADC kasi yung ating LSB, nakakontain niya lang noise. So parang, essentially, if nag-15-bit ADC ako, I'm still getting the same accuracy, but without the noise. Kasi hindi ko din naman nagagamit yung LSB ko pagka, 16-bit siya. So that is just a sample na application or scenario. And usually nga, if mas mataas na conversion time or mas mabilis na conversion time is mas mataas na resolution, it also usually means more power consumption. So that is something to consider. So in summary, ang analog to digital conversion natin requires sampling and quantization. So yung sampling, medyo hindi natin napag-usapan yung mga circuitry involved, pero ang kanyang function ay yung ito lang, yung meron siyang fixed na frequency and nakakapag-implement siya ng tinatawag na sample and hold. And then, ayun, our ADCs can be differentiated by how they quantize the input. So for example, here yung ating flash ADC, compare na lang yung input with all the available levels, digital levels na represented by yung ating resistor ladder ng sabay-sabay. Then yung SAR or yung counter ramp, isa-isa but in a ramp. And yung SAR natin, yung binary search, starting from the middle. And yun, binary search basically. So yan, we expect our very fast ADCs to be less precise and our very precise ADCs to be very slow. But something they have in common, ang very fast na ADC at ang very precise na ADC, mataas ang power consumption. And mataas din siguro ang presyo nila. So those are the things you would consider when you are going to use an ADC with your microcontroller. So most microcontrollers, meron naman silang built-in na ADC. For example, the PIC32 has a built-in SAR ADC. So medyo wala kang choice kung anong meron man sa loob. And that's all for this lecture video. And I'll see you next time.